Alright, good afternoon, Algebra 2 Trick Honor students. So today I would like to talk about combination and also the binomial theorem. So combination, last time we talked about the permutation, so this one is quite similar to the arrangement of permutation. So combination is an arrangement of selections of objects in which order it's not important. So it's called a combination. So think of combination as a grouping. So for examples of combinations, so things that order does not matter. So things that such consider choosing committees, topping, hands of cards. So the number of combinations of n distinct objects taken r at a time, it's given by n choose r, so c, so it's called choosing. So n choose r, so that equals n factorial over the quantity of n minus r, quantity factorial, times r factorial. Okay, so now to look at that, some of the problem here. So find the number of combinations. So n choose r. So 10 choose 6. So we do have 10 factorial over 4 factorial and then 6 factorial. The reason why that we end up with 4 because that's n minus r. So 10 minus 6 quantity factorial. So it's 4 factorial. So that's considered, well, I try to expand it. So try to reduce, and then you'll get 210. Okay, so the one that we have, so this one is like 10 times 9 times 8 times 7 times 6 factorial over 4 factorial, and then times 6 factorial. So basically the 6 factorial got reduced. And then 4 factorial, which is what? 4 times 3 times 2 times 1. So 4 times 3, 12 times 2, 24. So reduce with that 8. So that becomes what? 3. And then 3 goes into 9 3 times. So 10 times 3, 30. And then times 7. So 210. And then for that, a choose 3. So a factorial over 5 factorial, 3 factorial. So once you multiply it out, expand it, reduce, and then you get 56. So that one is a times 7 times 6 times 5 factorial over 5 factorial. And then times 3 times 2. So 3 and 2 and 6 got cancelled. 5 factorial got cancelled. So 56. So let's take a look at that, some of the word problem here. So a group of 7 students working on the projects. So need to choose 2 from their groups to present the group report to the class. And how many ways can they choose the 2 students? So 7 choose 2. So 7 factorial over the quantity of 5 factorial, 2 factorial. So it's 21. And you can order a hamburger with cheese, onion, pickle, relish, mustard, lettuce, tomato, or mayonnaise. So how many different hamburger could you build if you can only choose 4 topping? So a choose 4. So a factorial over 4 factorial, 4 factorial. So eventually, so this one is going to be considered a times 7 times 6 times 5 times 4 factorial. So one of those 4 factorial got cancelled. So denominator, which you have 4 times 3 times 2 times 1. So 4 times 2, that's 8. So a got cancelled. So 3 goes into 6 twice. So 10 times 7. So then that'd be 70 different way to choose. And the rest of this is quite similar, but to look at that, in how many ways can committee of 6 be chosen from 5 teacher and 4 students if they all are equally legible or legally eligible? So this one is what? 9 choose 6. So 84. Okay, so 9 factorial over 3 factorial, 6 factorial. And the other one, so the committee must include 3 teacher and 3 student. So if any kind of condition is given, so we need to choose 3 teachers, so 5 choose 3. And then since we choose 1 person, so that means there are 4 from the group remain. And then 4 choose 3, then that'll be 40. Okay, so this one consider multiplication with 2 combination. So here's another example. So your Algebra 2 class has 4 seniors, 10 juniors, 22 sophomore, and 2 freshmen. And you need to form a class committee of 1 senior, 2 juniors, 3 sophomore, and 1 freshman. And how many such committee are possible? So 4 senior, 4 choose 1, junior, 10 choose 2, and then sophomore, 22 choose 3, and then freshman, 2 choose 1. So once you come up with the results, so you want to multiply those numbers together. So eventually, so it's going to be totally 554,400 different ways to choose. So one of the classic example, it's about the deck of cards. So total we do have 52 cards. We don't include the jokers. So 4 suits, diamond, hearts, spades, clubs. And then 13 cards in each suit. So 3 faces card, king, queen, jack, and 10 non-face card, ace to 10. So how many diamonds are in the deck? So 52 divided by 4, so then that'd be 13. And how many red cards are there in the deck? 26, because the diamond and also the diamond and the hearts. And how many black face cards are there in the decks? So this one, let's see, how many black face cards are in the deck? So 3 times 2, then that'd be 6 black face cards. So then that'd be what? The jack, the queen, and also the king. Okay, so 3 times 2, so then that'll be 6. And then how many 7s are there in the deck? So 4. So how many possible 5 cards hand consists of all red cards? So 26 red cards, choose 5. So then that'll be 65,780. And how many possible 5 cards hand consists of all face card? So all face card total is what? 12. And then so 12 choose 5, so 792. So now for the rigorous problem, so 5 cards are drawn from a standard deck of cards. How many possible hands consist of 3 clubs and 2 diamonds? So 3 clubs and 2 diamonds, so then that'd be 13 choose 3. Again, the key word is and, so that means multiplying. So 13 choose 2. So 13 factorial over 10 factorial, 3 factorial, times 13 factorial over 11 factorial, 2 factorial. So multiply, finding the combination for the result, and then multiply them together. So it's 22,308. So the next one is quite similar. And then Shakespeare wrote 38 plays, and that can divide into three genes, okay? 3 genres of the 38 plays, and 18 are comedies, 10 are histories, and 10 are tragedies. And how many set of exactly 3 tragedy and 2 history can be read? Can you read? Okay. So this one, let's find out that the combinations. So then 10 choose 3 times 10 choose 2. So 10 factorial over 7 factorial, 3 factorial. And then 10 factorial over 8 factorial, 2 factorial. So 120 times 45, 5,400 different ways. Again, combination, the order does not matter. Permutation, the order does matter. So determine whether each situation involves permutation or combination. Then solve. So choosing 2 different pizza toppings. Again, different toppings, so that would be combination. Order does not matter. So 6 choose 2, 15. Arranging 7 shopper in line. Okay, so about lining up in the checkout counter. So order does matter. Permutation. So 7 pick 7. Creating words out of the letter in the word intercept. So this one is permutations with the repetitions. So intercept, so we do have, well, the word intercept, so we do have 2 pairs of letters that being repeated. So 9 factorial over 2 factorial, 2 factorial. And how many ways can 9 books are arranged on a shelf? So 9 pick 9, permutations, arrangements for lining up the books. And you have enough money to buy 3 books out of 20 that are on sale. And how many different set of 3 books can you buy? So this one, order does not matter, combination. So 20 choose 3. And then choosing a hand of 7 cards from a standard deck of cards consisting 5 cards from one suit and 2 cards from another suit. So 4 choose 1. Well, the reason why it's 4 choose 1 because that it consists with, okay, let's see right here, choosing a hand of 7 cards from a standard deck of cards. So the first suit, so that'd be 4 choose 1. And then the second suit, then that'll be 3 choose 1. And then 5 cards, so 13 choose 5. And then 2 cards, 13 choose 2. So we do have 4 different suits: diamond, spades, hearts, and clubs. So once you choose the first suit, so that means there are only 3 left. 3 different type of suit remain. So 3 choose another one. So for the first suit, you want to choose what? The same 5 cards, same color. So 13 choose 5. And then for the other suit is what? 13 choose 2. So for the Pascal Triangle, so anytime that I deal with the Pascal Triangle, so that means we're using it for the binomial expansion or the Binomial Theorem. So let's say that with the 0 power, so let's say that is like x plus y to the power of 0. So that means obviously the coefficient is 1. If that's like x plus y to the first power, we try to expand it. So this one is just like x plus y. And then if that's considered x plus y, quantity square, so then that'd be the third row. So x squared plus 2xy, and then plus y squared. As you can see that the coefficient right here, so we got 1, 2, and 1. And then if that's x plus y, quantity to the power of 3, then that'll be considered x cubed plus 3x squared y, and then plus 3xy, quantities y squared plus y cubed. So the coefficient would be considered 1, 3, 3, and 1. And that'll be this row right here. And then the rest of that to the power, so on and so forth, to the 4th power. So x to the 4th power, and then 4 x cubed, and then y, and then 6 x squared, y squared, and then 4 x y cubed, y squared, excuse me, and then the last one, then that would be y to the power 4. So this one is all about the binomial expansions. So this one can be also written as 0 choose 0 because the power is 0. And then the next one here, 1 choose 1. So the power is 1. And then the third row, 2 choose 0, 2 choose 1, 2 choose 2. So the power is square. And then the 4th row, then that'd be 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And then you end up with the exact same number. So the binomial theorem. For any positive integer n, the binomial expansions, a plus b quantity to the power of n, can be always expanded as n choose 0, a to the power of n, b to the power of 0, plus n minus 1 choose 1, a to the power of n minus 1, b to the first power, and plus so on and so forth, all the way to the last term. N choose n, a to the power of 0, b to the power of n. So the first term exponent started with 0, so the power goes down by 1 each. And then the second term exponent started with the power, and it goes up by 1 each time, while the second term, the second variable, it goes up by 1 each time. So the coefficient of the Pascal triangle, we replace that and choose r terms in the expansion of binomial. So for example, x plus 3 quantity to the power of 5. So using the Pascal triangle, we got 1, 5, 10, 10, 5, 1 for the coefficient. So started with the highest power, x to the power of 5, 3 to the power of 0, and then the next term here. So you want to lower down x with 1 degree, and then you want to increase the power of 3, so 3 to the first power. And then for the rest of the term here, same kind of pattern. So decrease the x base right here with 1 degree, and then increase the power of the base 3 by 1, and then so on and so forth. So once you simplified it all the way through, so you get x to the power of 5 plus 15x to the power of 4 plus 90x to the power of 3 plus 270x squared plus 405x plus 243. And then to the 4th power, similar. So it's 1, 4, 6, 4, 1 according to the Pascal triangle because the power is 4. So whatever the first term that you have, so you start with the leading coefficient as 1. And then For the next one, the power, you want to bring it down. And then for the new power, you want to subtract that by 1. And then for the next, the second term here, so you want to increase the power by 1. Okay, so the first term, always decrease the power by 1. And then second term, increase the power by 1. So that's what we got eventually. A to the power 4 minus 8 a cubed b plus 24 a squared b squared minus 32 a b cubed plus 16b to the power 4. To the fifth power, similar, using that the Pascal triangle, so 1, 5, 10, 10, 5, 1. So the reason why that we got 10, because that is like 5 times 4 divided by 2. So whatever the power that you have right next to each other, with the coefficients, you multiply it, and then you divide it by 2. And then find the coefficient indicated. So find the coefficient of x to the power 4 in the expansions of 2x plus 3 to the power of 7. So find the coefficients. So the x to the power 4 term. So try to expand it. So x to the power 7, x to the power 6, x to the power 5. And then the next one, x to the power 4. So this one is the quantity, 2x to the power 4. And also keep that in mind with the Pascal triangle. So we got 1, 7, 21, 35. So you need to follow through that, the Pascal coefficient as well. So 35 times 8. Because, well, 35 times 2 to the power 4, then that'll be 16. 16 times 35. And don't forget about that 3, the next term. It's what, 3 to the power of 3? Because that we're using power 4, so that means the rest of the power will be 3. The sum of those two power, it's always matching with the sum of the highest power. Okay, so that's why it's 3 to the power of 3 times 35 times 2 to the 4th power. So eventually, so the coefficient would be 15,120. We don't include the x right there, just the coefficient, because that's just a variable. And then find the coefficient of x to the power of 6. So once you expand it, so it's x to the power of 8, x to the power of 7, x to the power of 6. That means the third term. And then the third term for the Pascal triangle, so that the coefficient is what, 15? But don't forget about the second term. So if the power here is 6, that means the power for the second term would be 2. Because 8 minus 6, then that would be 2. So negative 2 quantity to the power of 2, so 4 times 15, which is what, 60. Again, this one is just find the coefficients. So I don't know why this one is being showed out with the variable. So that's a coefficient, it's just what, 60. We don't include the variable. So find the coefficient of x to the power of 3 in the expansion of quantity of 2x plus 5 to the 6th power. So again, if you try to expand this, 6th power, 5th power, 4th power, and then the 3rd power. And then from here, so we circle that, the binomial Pascal triangle coefficient. We're using 20. So 2 to the 3rd power, that's 8 times 20. Then that'd be 160. But don't forget about it's 5 to the power of 3. So 125. So 125 times 8 times 20. Then that'd be 20,000. So again, we don't need that, the variable. The variable is just the indicator for the term. So 20,000. Alright, that's it for the other part of the video today. So about the combination and the binomial with the Pascal triangle. Okay, so I'll see you guys next time.